Hello, my name is Bryce Boyle, and I'm a rising junior at Occidental College. Today I will be talking about my research on exploring models of feeling of knowing and memory retrieval. So I'm going to start off by asking a question. What is the capital of Pennsylvania? The capital is Harrisburg. Unless you are from Pennsylvania, it is likely that you may have gotten this incorrect. Many people would think of Philadelphia or Pittsburgh first and would have gone with one of those, since they are the two largest cities in Pennsylvania, whereas Harrisburg is the 8th largest. Most people associate the state with these cities due to the amount of knowledge they have about Philadelphia and Pittsburgh, since most people don't know much about Harrisburg. So what happened during this exercise? There's a cognitive science concept called feeling of knowing, or FOK for short, that occurs when you are aware of the likelihood that you know a piece of information before you actually think of it. So, a higher FOK means you are pretty sure you know something, and a lower FOK means you are less sure. If you did not get the Pennsylvania question correct, it is likely that you had a high feeling of knowing before thinking of your first answer, even though it was incorrect, because you were pretty sure you could name the capital. In my research, I wanted to create a simplified model of the mind and alter this concept of feeling of knowing in different ways in order to learn more about how it works in different contexts and how it changes over the course of answering a question. My research question was, how does feeling of knowing change throughout a memory search? I wanted to explore possible ways that people understand their own knowledge and how this understanding influences retrieval of information from their memory. I wanted to model potential FOK calculations because of how efficiently and accurately humans can recall information, and because there is not one agreed upon method for finding FOK in cognitive science. Through creating these different calculations, I will be able to look into how different methods of computing feeling of knowing perform when applied to different tasks and how it changes throughout a memory search. This research is important because cognitive scientists have not defined any one calculation that accurately reflects human feeling of knowing, and exploring this phenomenon through cognitive modeling will eventually give us a better understanding of human memory retrieval. This concept can also be applied to the field of artificial intelligence for implementing a more realistic memory search process. Before I explain what I have been working on, I want to introduce some key concepts in cognitive modeling and how they apply to computer science. Memory retrieval is thinking of something you know. It can occur when you are asked a question or if you are just thinking unprompted, but it is simply the process of recalling information in your memory. In the Pennsylvania question I asked, a memory retrieval was done when you came up with an answer. The cue in a retrieval is what you are asking a question about, and the target is the answer you were looking for. In this example, Pennsylvania would be the cue and Harrisburg would be the target if you got the question right. Otherwise, the target would be whatever answer you came up with. Next, metamemory is the awareness of one's own knowledge and memory systems, and metamemory judgments are judgments made based off of this awareness. These judgments include how well you think you've learned something, the tip of the tongue feeling you get when you just can't quite give an answer to a question, and how confident you are in your answer to a question. For example, asking yourself, "What is my knowledge of Pennsylvania?" is a metamemory judgment. Another type of metamemory judgment that I have focused my research on is feeling of knowing, as I mentioned earlier. Again, it is a judgment as to whether a piece of information is known that is made before actually retrieving that information. Going back to the Pennsylvania example, an FOK judgment occurred right after I asked the question, but before you answered it. The judgment was based on how likely is it that I have an answer to this question, which determined whether you knew enough about cities in Pennsylvania to start thinking of an answer. If you immediately knew your knowledge of the state was too limited to even bother trying to answer, your feeling of knowing would have been very low. Without this judgment, you would have wasted your time searching through the things you know, desperately trying to find the capital of Pennsylvania, even though you would probably never find it. Applying these ideas to a cognitive model, here's a simplified visual representation of the knowledge base for the Pennsylvania question I asked. In cognitive modeling, memory is modeled through a data structure called a graph, which is made up of nodes and the connections between them. Each piece of information in memory is a single node, and the connection, or edge between them, is how they are related. In this model, memory retrievals are done in the form of a query, where an answer is found through the edges connecting the concepts of a question. Like I stated earlier, feeling of knowing measures how likely it is that the desired piece of information exists in the graph of memory at all, and is calculated before an answer is found. To explore how feeling of knowing changes throughout memory retrieval, and to determine what approaches to calculating FOK may produce realistic results, I created 5 FOK algorithms based on existing work and tested them on a series of memory retrieval tasks. Not every FOK algorithm I'm using will work with every question because of how knowledge is set up in each case. However, that is why I'm running many different tasks and analyzing the results. Some related work and existing hypotheses about FOK that have influenced my research includes these 4 cognitive science ideas. FOK may be based on cue familiarity, or how much is known about the subject, accessibility, or how frequently and recently information was recalled, or competition. How many distractions are there while finding information? It is likely that all of these and more factor into calculating FOK, as some research has found, so I coded up 5 specific methods of modeling FOK based on these existing hypotheses. Accessibility is one thing that will factor into most of my algorithms, which is made up of frequency and recency. Frequency is how many times you have recalled information, and recency is how recently it was recalled. For example, how many times have I thought about cities in Pennsylvania? When was the last time I thought about this? If you have thought of a piece of information more recently, you're likely to remember it more clearly. Similarly, if you have thought about something many times, you will be able to think of it again pretty easily. Taking this into account, accessibility is the combination of how frequently and recently information has been recalled. So, a piece of information would be highly accessible if it had been recalled many times not too long ago. In my program, something called activation represents accessibility. The activation of a node is calculated based on the number of times and how recently it has been recalled. Activation spreads across nodes of the graph through the edges that connect them. For example, recalling Pennsylvania in the question, "What is the capital of Pennsylvania?" would activate the nodes it is connected to. Then the activation of those nodes would spread as well, and so on. The amount of activation that reaches nodes further from the starting point is significantly less than the first node's activation because it decays over time. Applying this to the example graph again, recalling Pennsylvania should boost the activation of Carnegie Mellon University less than it boosts Harrisburg or any other node more closely related to it. Harrisburg is 1 step away from Pennsylvania, while Carnegie Mellon is 2 steps away. The first 2 FOK algorithms I implemented are based on activation. In this calculation of feeling of knowing, the activation of the cue is factored in, and nothing else. If one was asked for the NFL team based in Pittsburgh, the FOK made before recalling the answer would be the activation of the cue, Pittsburgh. This next algorithm using activation compares the activation of the cue I just mentioned to the average activation of all nodes in the graph. If I now asked for the capital of Pennsylvania again, you would take the cue's activation at this moment, which would be the activation of Pennsylvania, and divide it by the average activation of all nodes to find the relative activation FOK. The next set of algorithms incorporate the idea of familiarity. Familiarity is how much information is known about the general concept of a piece of information. In the Pennsylvania example, this would represent how many other things you know that have to do with Pennsylvania. Naturally, the more you know about something, the easier it will be for you to think of it. In computer science terms, familiarity can be described as how many edges are connected to a node. The overall concept of Pittsburgh in the graph includes all of the information known about it, which is 4 other nodes, while Harrisburg is only connected to 1 other node, so its familiarity is much lower. The third FOK algorithm I created uses this idea of familiarity. It takes the number of edges connected to the cue node and compares it to all other nodes' edges. In this example, the relative edges FOK for this question would be the number of edges coming out of Pennsylvania divided by the average number of edges per node in the graph. This next algorithm uses both familiarity and accessibility, or activation, by dividing 2 ratios to find the relative activation over the number of edges of the cue node. The first ratio is the cue's activation over the number of edges connected to it, and the second ratio is the average activation over the average number of edges per node. Finally, this competition FOK algorithm goes against the idea that the more edges from a node, the better. Rather than more edges from a node being helpful, they are more distracting, and that makes it harder to find one specific piece of information. For this final algorithm, I'm going to continue with the Pennsylvania example, but with a different setup. If I asked you to remember Pennsylvania when I ask you for a US state, and ask you to remember Harrisburg when I ask you to remember a city in Pennsylvania, you would be more likely to give me Harrisburg when asked for a city than Pennsylvania when I asked you for a state. It would be difficult to find one in the 49 other states in memory, while looking for a specific city in Pennsylvania would be much easier since there are only 3 options in memory. So overall, even though you have a limited knowledge of 3 cities in Pennsylvania, you are more likely to be able to retrieve one of them than a specific US state. Feeling of knowing can also be historic in that it takes into account past FOK judgments made. I will be keeping track of the history for all FOK methods I'm running. For example, if you did not guess the capital correctly, the FOK you would have before your next guess would be lower due to the incorrect answer you just gave. If the next answer was wrong as well, your previously low FOK will cause your next FOK to be lowered even more. In terms of coding this up, determining historic feeling of knowing requires keeping track of past FOKs throughout the retrieval process and factoring them into the newest calculation, which was done using a series of weighted averages. Now that I have talked through the setup of my model and the algorithms I used, I will discuss how these algorithms were tested on different retrieval tasks. These tasks include a paired recall task from a psychology study and a set of more complex multi-step questions that show patterns FOK may follow throughout a thought process. I will use the results of these experiments to see whether my algorithms successfully match expected human thought processes. The first task I ran my algorithms on is a recreation of a paired recall psychology experiment done by Liebert and Nelson. In their paper, the relationship between feeling of knowing and recall was tested through a series of experiments. Participants were split into 4 groups. Each group was told to remember a pair of deliberately unrelated words, the A and B words. Then they were shown another pair of words. The first group was shown the A-B pair of words twice, and the second group was shown the C and B words as a pair. The third group was shown the C and D words, and the last group was shown the A and D words as a pair. The results demonstrated that when recalling the original AB pairs, the first group who saw the AB pair twice had the highest FOK, while the other groups had lower but still similar FOKs. I wanted to mention that historic FOK will not be calculated in this task because of the simplicity of this experiment. There is really not history to keep track of since the retrieval is done in one step. The expected results of this experiment are shown at the top, with ABAB having the highest FOK, and all other paradigms having lower but similar FOKs. In my results, I was not looking for similar numbers, but rather the trend of ABAB having the highest FOK and the others being lower but similar. None of the FOK algorithms tested on this experiment produced similar results. However, for 3 of the algorithms, activation FOK, act over edges, and competition, ABAB is generally on the higher side, but at least one of the other paradigms are just as high. In addition to exploring models of feeling of knowing that could produce similar results to the AB experiment, I wanted to look at how different models could affect recall in more everyday situations. I used a number of Jeopardy-style and multi-step questions to test my FOK algorithms with, where the Jeopardy questions were fairly simple and the multi-step questions were more complex, requiring a longer thought process. An example of a one-step question would be, what is the capital city of Pennsylvania? And an example of a two-step question would be, what is the population of the capital city of Pennsylvania? Since you have to first come up with Harrisburg and then think of its population. The multi-step questions I asked contained about 3 to 4 steps each in order to track how FOK changed over time. Here's an example of one of the multi-step questions I created and ran my algorithms on with an estimated thought process. The question is, what is the capital of the nation that is hosting a major international sporting event in 2028? The first step to answering this question is finding something in memory that is a major international sporting event occurring in 2028. Based on that information, one may either think of the 2028 Euro Cup or the 2028 Olympics. If the Euro Cup was the chosen answer, the next step would be to find what city is hosting it. However, since that information doesn't exist in memory, the search would stop and go back to the next node that was a major international sporting event, which would be the 2028 Olympics. From there, the search would continue by finding the host city, then the country that the city is located in, then finding the capital of this country as the final answer. Running FOK experiments on complex questions such as this one demonstrates how feeling of knowing changes throughout the memory search process and helps narrow down which algorithms match the expected human thought process. It also allows for the historic component of FOK to build on itself and become more meaningful over time. For this Olympics question, 3 methods produce the results I would expect to find in a human thought process. In this graph, the x-axis displays the time throughout the memory retrieval, and the y-axis displays the feeling of knowing. At first, FOK should be relatively high, since multiple international sporting events occurring in 2028 are known. Then, after the Euro Cup is guessed incorrectly, FOK lowers for the next step. After this, FOK continues to lower as the location of the 2028 Olympics is found. Then FOK should increase because of increased knowledge of Los Angeles and the United States. The 3 methods that followed this pattern were relative activation over edges, and absolute activation, shown in green, red, and yellow respectively. The black line shows the trend that I would expect for this question as I just described, and the dashed lines represent the historic version of each method. As you can see, none of the historic counterparts to my algorithms fit the expected trend. Relative and absolute activation were likely successful because my knowledge graph was quite small and almost all of the nodes in the graph were used to find the answer. There were no unrelated nodes to alter relative activation in any way, and absolute activation followed the trend because of how activation spreads throughout the query. Similarly, the relative aspect of relative activation over edges was not very influential to the calculation. The edges or familiarity-based FOK algorithms did not follow the trend, most likely due to the limited number of edges in the fairly simple knowledge base. These are the FOK over time graphs for 2 other multi-step questions I ran my algorithms on. The first one was, what is the predominant color of the flag of the country that built the largest man-made structure in the world? The answer is red because it's the Great Wall of China in, China, and their flag's predominant color is red. This may start out with a low FOK because it may take a few tries to figure out what the largest man-made structure is, but after that, the rest of the information should be fairly easy to find. The second question was, Indonesia's Mount Marapi, whose name means fire mountain, is one of these, and the answer is volcano. I would expect the FOK for this question to begin fairly low or at 0 as one searches through their memory for information about Indonesia and Mount Marapi. Assuming that wasn't enough to get the answer because of a limited knowledge of these things, one would try to think of more things about fire or mountains, and then from there, they would be able to draw the connection between the two and have a higher FOK and figure out that the answer is volcano. To summarize, it was found in the A/B task that no algorithms fully matched the trend found in the experiment. However, absolute activation, relative activation over edges, and competition FOKs were the closest to matching. For the multi-step questions, one algorithm alone did not give consistent results across all questions. Further, I have found no current literature approaching FOK as a dynamic measurement that changes throughout a thought process, as it does in my model, and I believe this idea should be further explored. Despite having none of these algorithms work on their own, the goal of this project was to explore different methods of calculating feeling of knowing, and this has helped to narrow down what algorithms should be focused on in the future. In the cognitive science field as a whole, there is not a single agreed-upon mechanism for creating feeling of knowing, so it makes sense that a combination of these algorithms must factor into FOK, but that not one does it alone. Some next steps that could be taken with this research include creating and testing more complex combinations of FOK algorithms, exploring FOK as an ongoing process, applying my algorithms to a larger knowledge base so that it more closely represents a human mind, looking into how FOK influences what strategy you use to think of information, and applying FOK to artificially intelligent agents for a more realistic memory search. Thank you for listening, and feel free to contact me if you have any questions.